Okay, well, good afternoon, everyone. Thank you very much for joining us this afternoon for this very interesting talk. So before I introduce our invited speaker, Professor Karen Scrivener, I would like to give just a brief introduction about the Transforming Foundation Industries Network Plus. Today, we're going to give one of our seminars part of the webinar series of Blue Skies Green Futures. Next slide, please. Next slide, please. Thank you. So just to give you a brief introduction, the Transforming Foundation Industries Network Plus was created in January this year and is a new initiative that is led by the University of Sheffield, University of Leeds, University of Manchester, and Swansea University. So the director of our network class is Professor Ian Rainey from the University of Sheffield. He specializes in glass and ceramics. Professor William Sampson from the University of Manchester. He specializes in paper. Professor Cameron Playdell-Peirce. He specializes in metals, particularly steel, and he's also the co-director of the Sustain Hub. And myself, Susan Bernard-Lopez, I'm Professor of Structural Materials at the University of Leeds, and I represent the cement and concrete sector within this network. So as part of the network, we have an industry advisory panel. The chair is Chris McDonald. He's the CEO of the Materials Processing Institute, and also we have a fantastic management team. We have Debbie Froggatt, she's a marketing officer, and we have Neil Laurie, our network manager. Next, please. So the core aim of the Transforming Foundation Industries Network Plus is to identify and co-create with the foundation industries new science and technology that will enable transformations towards more sustainable, cost-efficient, and product practices. So it's more a holistic approach to promote industrial symbiosis and identify commonalities between different foundation industries to promote sustainability practices. So at the moment, we're working towards 6 themes. One is resource efficiency, next generation processes, manufacturing informatics or digitalization, circular economy, and advocacy, equality, diversity, and inclusion. So we're very proud and most grateful with all the support we have got for the past months. At the moment, our network comprises 420 members, which is incredible considering how young our network is. That is well balanced between industry and academics. So we were very fortunate that we were granted funding by the Engineering and Physical Sciences Research Council to open different calls to sponsor like a small projects or seed corn projects that can lead to major initiatives for transformation in foundation industries. So at the moment, we have already funded 6 research projects around £270,000. We have just closed our second call, and hopefully we will be announcing the people of the next 6 research projects in the next few weeks. So next slide, please. So as I mentioned before, we are a very new initiative. We just started in January this year. Our first exercise was having a look to the road mapping of all the different foundation industries and also different roadmaps that have been developed thinking about resource efficiency, energy efficiency for all industries overall, not just looking at those in the UK, but also Europe, but also other roadmaps that can be relevant for us to identify what has been done, what is planned to be done in the future, and how can we integrate all these different ideas to create a more integrated, like symbiotic roadmaps that can benefit different industries. So our second workshop was on energy efficiency processes, and that was also feeding us some information about what are the needs of these industries and what the industries want us to support with the upcoming funding calls. So our third workshop was in resource efficiency and circular economy, and our most recent workshop, actually last week, was a digitalization workshop with the KTN. So as I mentioned before, we had different calls, and we will be opening new calls in the upcoming months. And then as part also of our outreach activities of the network, we created this Blue Skies Green Futures webinar series, where we are aiming to showcase groundbreaking technologies for the foundation industries. Final slide, please. So for those that are new to the network class, you're most welcome to send us an email with our email address if you have any question, or when we open the calls, if you have any interest to get further information about the scope. Also, you can join us. It's a very easy process by our website. It's just a couple of minutes, a short form that will give you access to a special site that is for members, when we are sharing all the recordings of the different meetings and all different information. And of course, you can keep up to date with all our news and information that we share following us in social media. So completing that, I'm very pleased now to introduce Professor Karen Scrivener. I think Karen is a person that doesn't need much introduction. She's very well known in the cement and concrete research area. So Professor Scrivener, she is the director of the Construction Materials Lab in EPFL. So she's also the chief scientific officer of the Global Cement and Concrete Association Network, the Innovandi Network. Well, Karen has been a pioneer in many different initiatives, leading transformation in the cement and concrete sector, particularly collaborating very closely with the industry to drive all these different initiatives to fruitful implementation. So thank you very much, Karen, for accepting this invitation today. So if you can please share your screen, the floor is yours. Sorry, Karen, you're muted.
So thank you, Susan, for this introduction. Just to correct one thing, I'm not the Chief Scientific Officer for Innovandi. I'm the head of the scientific committee. So I mean, I'm just playing an honorific role to coordinate the academic partners of this network. So it's very nice to be talking to you today. I was a little bit worried this morning that many of you will have heard this talk before, but looking through the list of participants, there are only quite a few names I recognize. So maybe we have some people outside the cement and concrete world. So really what I'm going to talk about today, I mean, we know we're now facing this climate emergency. We know the target has to be to go to net zero emissions by 2050. And, you know, what in the context of cement and concrete, what can we do? As a first thing, I have a little quiz. So we're not going to be able to do this interactively because it's not going to be practical with this number of people. But maybe you can just think about it. So which of these sectors has the highest annual CO2 emissions? So of course we have cement and concrete, we have iron and steel, we have clothing, we have passenger transport by road. So that's not freight transport by road. And food loss, food waste. So you can just sort of think about that for a minute, which one you think has the highest emissions. And I think the answers might be surprising to some of you. So of course, cement and concrete, we know, is somewhere in the range 6 to 8%, but iron and steel is almost the same. What I found was 7%. I think the one that's the real eye-opener is 10% is coming from the clothing industry. And, you know, perhaps in terms of things we can do to reduce CO2 emissions, like we know we should eat less meat, perhaps we should also think about buying less clothes. And then, of course, passenger transport on the road is 9.5, and food loss, food waste is also another big surprise, up at 6%. Now, I mean, I'm not saying that this means that, you know, you shouldn't do anything on cement and concrete, just the opposite, because net zero means net zero. It means that all these figures have to go to zero. But I think it just highlights, you know, where CO2 emissions are coming from and what we need to do. Now, the fact that the emissions from cement and concrete is so high is purely and simply related to the amount of these materials produced. So these was quite old figures we published in our report in 2015. I think even then they were an underestimate. Today, the estimate of the amount of cementitious materials, that's to say cement, concrete and mortar, is about 30 billion tons. That's certainly more than all other materials put together. And purely from a resource standpoint, it's clear that we couldn't significantly replace it with any of these other materials. And I certainly don't think we should see it as a competition, because we certainly need all materials. You know, people want to promote timber as a solution, and, you know, timber can be a very good building material, but we have no means to significantly increase this. Because if we wanted, say, to replace just 25% of the emissions from concrete with timber, we would have to plant a new forest 1.5 times the size of India. And this, even if we could do that, which clearly we can't, that would actually have no impact by 2050, because, you know, the trees would hardly be grown by 2050. So, you know, we need to stop people thinking that timber can just solve everything if we stop using concrete. It's simply impossible. And more importantly, you know, in developing countries, there's still a huge, huge demand for people to be housed decently. Just in Africa, it's predicted another 200 million houses will be needed in the next 10 years. No, I shouldn't say houses, I should say accommodations or homes should be needed in the next 10 years. So this is a huge problem we have to solve. And if we don't solve it, we know the consequences. People from these countries, they have nothing to lose, so they just want to migrate to our countries. And from an intrinsic point of view, we also have to realize that the embodied emissions and the embodied CO2 of concrete are some of the lowest of all materials. These figures here come from the book of Mike Ashby, and you can really see concrete is right down in this bottom corner. Here are metals, here is timber, here is glass, and plastics right up many orders of magnitude higher. So concrete is essential, but we can do a lot to improve it. And we made a first attempt to evaluate that in 2016 with this UN Environment Report. I think things have changed really, really a lot in the 5 years since we brought out this report, because 5 years ago, the level of emissions reductions was forecast to be necessary, was forecast to be quite modest. Now, because we've done nothing, we're in a much more serious situation. We have to go much further, and we really have to meet this net zero. So, you know, the things are much more serious. Now, cement is often called the hard to abate structure for the simple reason that the majority of the emissions come not from energy. So this shows you a cement kiln. It looks like a kind of rusty, inefficient old process, but that's really not true, because there's been tremendous improvements in efficiency of cement making, mainly since the first oil crisis in the 1970s. So very simply, the oil price went up 4 times. The cement industry scrambled to use less oil. And by and large, they've been very successful in this, improving efficiency dramatically, and particularly in Europe, incorporating waste materials, so that in European countries, many, many plants are operating with more than 80% of waste fuels. So the 60% of emissions that's left is coming from this simple chemical reaction, which is the breakdown of limestone. So 80% of the raw material to make cement is limestone. And what happens when you make cement, you start to heat this up. And the first thing that happens is you have this decomposition of calcium carbonate into calcium oxide and CO2. And about 60% of the emissions are coming from there. So, you know, that's not so easy to solve. The other thing in terms of the context I want to highlight is that even today, and certainly in the future, a very small proportion of cement production is coming from OECD countries. You know, we often sit around in our nice, comfortable offices and homes and consider these very elaborate, sophisticated potential solutions. You know, that's not going to address the problem. We're only going to address the problem if we can provide solutions that can be used by everybody, and particularly in the countries where the demands for homes is going to be so enormous in coming years. We've seen what's happened in China in the last 30 years, such that China now consumes more than half of the world's cement. This figure is certainly going to decrease, but there are other countries coming online like India and many other countries, notably in Africa. So today in India, the cement consumption per capita is about 5 times less than in China. In Africa, it's even half that again. So you can see the amount of pent-up demand there is in these countries. And these have got to be the countries we engage with if we're going to bring about these lower CO2 emissions. So again, if we relate this back to this figure of how many emissions are coming from cement, it's incredibly varied country by country. United States, for example, which has quite a low per capita use of cement and a very, very high emissions in terms of energy from transport and everything like that, it's probably only about 1 or 2%. Whereas in a country like Vietnam, which produces a lot of clinker, and a lot of that is in fact exported, it may be up to 25%. Now, I really want to stress the point here that there's no one single solution. We need to work at all the different levels if we're going to reduce emissions the way we need to. And this shows simply the value chain that we need to reduce the clinker from CO2, so CO2 from clinker production. This has largely been done to the extent possible. We then need to reduce the clinker in the cement, and that's mainly going to be what I'm going to talk about today in terms of substitute material. We need to reduce the cement in concrete, and that's a very important lever that really has been very little studied. I'll say a little bit about that at the end, but we can go further. We can reduce concrete in buildings. We can use buildings more efficiently rather than demolishing them. And of course, if we have to demolish buildings, we can recycle. Concrete is a perfectly recyclable material. It's the only obstacles are really cost and logistics. In technical terms, every single part of concrete can be reused. And in this report we wrote for the European Climate Foundation, we calculated that if we really strung together these possible savings, we could imagine reductions of up to 80%. I'd like to emphasize that there's no such thing as a zero CO2 cement unless you also have some carbon capture and storage. But we know carbon capture and storage is by no means a panacea because it's not in place yet. It's going to be very expensive. And there's going to be a lot of social resistance to storage sites. And, you know, we cannot just hide behind the fact that carbon capture and storage will be needed and say that's the solution to everything, because it's not a solution that's there now, and we have to have reductions. So all these things are really what need to be worked on first, and then carbon capture and storage has to be a last resort. Now, I explained to you how most of the CO2 emissions are coming from limestone. And of course, then question most people ask is, well, can we avoid using limestone? And that's a very interesting question. The short answer is no, but I want to try and explain to you why. The main reason why is because of the composition of the earth. So we live on Earth. it's a planet. The composition comes from what happens in stars, the way that they burn, producing helium over most of their life, and then in the last fractions of their life, heavier elements. And the really heavy elements beyond iron only get created in explosions like supernova. So this is why more than 98% of the Earth's crust is composed of oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium. And clearly, for something that's used in such enormous quantities as cement, it makes no sense to explore the chemistries in this remaining 2%, because these materials are not going to be available in the quantities we need. They're going to be way too expensive. So to see which of these elements can be suitable, we need to think quite simply about how cement works. And on the simplest level, it is quite a simple process. It's almost, in fact, magical the way it just works, and we never think about how it works. And we've still got a lot to learn about the detail, but in essence, what happens is this. We start off with this gray powder, these gray grains, which are just floating around in water. And that, of course, gives us something we can put in place, make many different forms out of. But what's happening is that those gray cement grains are dissolving. So like when you put sugar in your tea or salt in your potato water, they dissolve. But then we get something that's very different from salt or sugar dissolving, is that the different ions that form this cement can then make new combinations together. And these new combinations of ions can precipitate. And the precipitates, I've drawn in red here, they're what we call hydrates. And these hydrates bridge the spaces between the cement grains. They have a larger volume than the amount of solid that dissolved, for the simple reason they incorporate the water in their structure. So water now becomes part of the solid. And this is why it increases in volume. And you can start to fill in the space. You never completely fill in the space. You still have pores there. But that's what gives you this strong and durable solid. So let's go back and look at these different elements. Well, most of these 7 here are actually combined as oxygen. So if we consider the oxides of sodium and potassium, the problem we have here are these are way too soluble. We know that we can make strongly alkaline solutions by dissolving sodium and potassium in water, and then we don't hardly ever get precipitates. On the other hand, the oxides of iron and magnesium, they're too insoluble. So they don't move around. If you examine an old cement paste, you can see quite easily all the places where the iron was originally in the cement grains, and in however many years you look at it, doesn't ever move anywhere. It just stays in the same place. So it's not really contributing to this process of filling space. And the same with magnesium. When you have even very small amounts of alkali present, it doesn't move around. And, you know, if we have a slag cement, then the slag is basically staying in the same place. So this takes us from the overall composition of the Earth to a system of just 3 oxides: calcium oxide, silicon dioxide, and alumina. And we know this system very well. It's been studied for more than 100 years. And we know that basically there are only 2 areas of this diagram where we get cementitious materials. We have this area here, which is the region we call Portland cement, which is basically calcium silicates. We also have this region over here where we have calcium aluminates, calcium sulfoaluminates. And at first sight, this appears very interesting because it's much further from this calcium oxide corner. And that means that you need less limestone. Less limestone, of course, means less CO2. And if you produce cements in this region, they can have CO2 emissions some 20 to 30% less than Portland cement. However, life is not so simple, because then we have the problem that to produce compounds in this region, we need to have much higher concentrations of alumina compared to silica. And these minerals are much rarer. We have bauxites, but, you know, bauxite is used to produce aluminium. And even if all the current bauxite production was diverted, we would still only replace 10 to 15% of current demand. And then people say, well, you know, there's lots of waste products with aluminium in. Well, that's true. But what people call lots in terms of waste is often very, very small in terms of cement production. And that's the case here. The kind of waste streams that contain the amount of alumina needed are available in quantities which are really absolutely minuscule compared to the world demand for cement. And, you know, I think we see the proof of this, that these cements were pushed very, very strongly in China from the 1970s. But today the production in China is less than 1,000th of Portland cement production, and it's actually going down. And that's without talking about the many technical difficulties of these materials. So what other possibilities do we have? Well, you know, this is a bit the problem, that all these roadmaps people are coming up with, they try to evaluate what can be done, and then there's always some gap. So they say, well, we're going to have some wonderful breakthrough in the future, or we're going to do carbon capture and storage, which is fine. But I mean, you know, what breakthroughs can we really have when we know what the composition of the earth is, and clearly that's not going to change. You know, if we consider cement as a solid material, I think that, you know, imagining there's something out there we don't know about verges on magical thinking or alchemy, that we can suddenly transform these common elements into something else. And, you know, we have to realize people cannot live in nano or virtual houses. We've seen tremendous advances in the miniaturization of electronics, but we've seen exactly the opposite in terms of houses. People want to live in bigger and bigger houses rather than smaller and smaller ones. And, you know, there's frankly a lot of ideas going around there which border on, you know, untruths. So that one of the most common fallacies comes from this cycle we have. You know, I've explained to you that, you know, we have limestone, and most of the Earth's calcium is tied up as limestone or other minerals, which is very difficult to separate the calcium from. And during the production, that breaks down, it gives off this CO2 in the atmosphere. And then we have this hydration process I explained to you very briefly, and it forms calcium hydroxide. And over time, those hydrates will reabsorb the CO2, the concrete carbonates. But of course, it's fairly clear that the amount of CO2 that's reabsorbed here can never be higher than the amount of CO2 which was given off in the first place. And worse than that, you know, we're now in a very urgent situation where we have to reduce to zero in the next 30 years. And this process is a very slow process, taking tens or hundreds of years. So it's going to have very low significance in the time scale we're talking about. So there are people who come along, and, you know, these people have had very good finance for their projects, based on the idea that if we add calcium oxide or calcium hydroxide to cementitious materials, it will react with more atmospheric CO2. And it will. But where do you get the calcium oxide or calcium hydroxide from? Basically, they all come from limestone, and they've given off their CO2 in the process, and they're never going to absorb more than they gave off in the first place. People talk about uncarbonated sources of calcium oxide, but, you know, we're making some attempts to evaluate that. But, you know, just even on a first look, you can see that this is really tiny amounts. It's the same problem as alumina waste. You have quantities, but the quantities are really small and will not make a significant difference on world CO2 emissions. Then we have people who come up with even more elaborate ideas. They say, this is wonderful. We have these microorganisms, algae, bacteria, which can take CO2 and form calcium carbonate. And this is true. There are a lot of these organisms. This is the way limestone formed in the first place. Limestone formed over millennia by organisms fixing CO2 in their skeletons. But of course, to fix CO2 in their skeletons, they need also a source of calcium. So if you take these bacteria into your factory and try to get them to produce calcium carbonate, you have to feed them a source of calcium hydroxide or calcium oxide. And the same argument applies, that where do you get that calcium oxide from? So, I mean, whenever I explain this to people, they all understand it very clearly and even laugh that people can come with such ideas. But I tell you, there are many, many companies out there which are peddling this as a solution. And if you do have sources of uncarbanated calcium, well, you actually can use them very simply just to make cement and reduce the emissions from the cement. And then we have alkyl activated materials. I'm not going to go into these in detail, but the problem of these alkyl activated materials is they're based on generally slag or high calcium fly ash. It's only the ones with some content of calcium that really work in the field at room temperatures without very, very high amounts of alkali. And the basic problem we have is that slag, for example, we have only 8% compared to the demand for cement. And 95% of that is already used in cement and concrete. So if we divert some slag to producing alkyl activated materials, it's true that particular material may have lower CO2 emissions, but overall worldwide, we've done absolutely nothing. In fact, we've probably increased CO2 emissions because we had to produce the alkylite activators to use these materials. And that's without talking about any technical problems which still exist. And, you know, I hate to say it this bluntly, but, you know, we've really wasted billions of dollars on these technologies over the years. So when we look at all this, we really have to face the fact that Portland cements will continue to dominate. And the way we can reduce CO2 emissions really dramatically is, of course, to replace the clinker with other things. And that's not new. We've been doing it for several decades. This graphic here shows you the level of substitution materials from the companies that are members of the Global Cement and Concrete Association in their Getting the Numbers Right database. So it may seem quite a low proportion, but I think it's actually quite typical of what's going on worldwide. And of course, we see some substitution with gypsum, which would kind of ignore that because the gypsum always has to be there. Then we see that the most used substitution material is limestone, then we see slag, and then we see fly ash, and then we see pozzolans. Now, what's important in this graphic is that you see nothing has changed in the last 10, 15 years. And we already see in this graphic how the amount of slag available is going down. And it's going to, that trend is going to continue because both slag and fly ash come from very CO2 intensive processes. Burning coal is the first and foremost thing we have to stop in order to confront the CO2 crisis. So fly ash is going to disappear. Most roadmaps estimate 0 fly ash in the year 2050. Slag, similarly, because we're recycling more steel, which is of course very good. The more steel you're recycling, the less you have to obtain from iron ore. And of course, eventually we're going to see other methods of reducing iron ore to iron. This can be done, for example, with hydrogen, which is a very good prospect. So slag is going to disappear. And most of the cements in the world already today are in fact blended cements. There's some countries like notably the UK and North America where they like to add these additions at the concrete level rather than the cement level, but it amounts to the same thing. So this is basically what I've already said. Slag and fly ash are disappearing. They're only 15% of cement demand today. They're not available in those countries where the demand is going up most strongly, like Africa. And then people have studied a number of other things like vegetable ashes, for example. The long and short of it is that these are really small amounts of material. They can be used, but they're going to not make much dint in the CO2 emissions. Limestone, of course, we have a lot, but the problem with limestone is it's only reacts a little bit in normal cements, so that when you have additions above about 15 to 20%, it just becomes a diluent, and then you end up having to use more material in the concrete. So the thing that can really change this, in fact, the only thing that can really change this are clays which you can calcine. And this is what we realized some 15 years ago. We started to work more on calcined clays. Of course, calcined clays were known. It wasn't, you know, I mean, it wasn't completely original by any means. It's well known that clays, when you heat them up, become very good pozzolans. But what we found out, which was really, I think, a game changer, is that we could have this synergistic reaction between calcined clay and limestone. And because of this synergistic reaction and the fact that limestone is very low CO2 material, you could actually go to very high levels of substitution and high levels of CO2 reduction. So this LC3 technology, as we call it, LC3 stands for limestone, calcined clay, cement, is actually a family of materials. We often use a number like, you know, 65 or 50, where that's the amount of clinker. And if we take this LC365 and we just mix the materials together in the lab, we see that we have slightly lower strength at 1 day, but by 7 days, the strength is higher. And this is just mixing together in the lab. But if you do it properly in a cement plant, you can get even similar strengths at 1 day. So we've got 50% less clinker, 40% less CO2, similar strength, better chloride resistance, resistance to alkali silica reaction. And we can get these high replacement levels because of this layer structure of clay. It's not like slag or fly ash, which are glassy materials. It has this layer structure, and the kind of clay we need, which is kaolinite, has this one-to-one structure with 1 layer of silicon and 1 layer of alumina. And when you calcine it, you disrupt the structure, and both of these can be available. And it's particularly this alumina in the metakaolin, disruptive structure, which can react with limestone to give space-filling hydrates. And we now tested more than 70 clays from around the world. We find that the parameter that really determines the strength development is the kaolinite content. These red lines give the reference strength of the Portland cement. So you see you can match the reference strength of the Portland cement with only about 40% kaolinite. And these kind of clays containing some kaolinite are super abundant. This shows you clay maps from this publication in Scientific Data, and you can see this kind of orangey browny color really in many parts of the world, and particularly in those parts of the world where this demand for cement is going up. And often in these countries, they're actually waste streams. This is a quarry from India, where this is clay from the overburden, which is not suitable for the original purpose, but very suitable for making cements. And, you know, if we compare these calcined clays to conventional SCMs like slag and fly ash, either in binary mixtures as 30% substitution or in ternary mixtures with limestone, you can see at the end of the day, they all have very similar strengths, but the big advantage of the calcined clay is they develop the strength much higher. So if we go back to this figure here from the GCCA members, and we imagine now that instead of the clinker substitution level stagnating at about 20%, we could easily go to a substitution level of 40%, then we would save 400 million tons of CO2 per year. And I think this is a conservative estimate. I think we could actually save maybe double that. These are some recent results of ours, where if we look here, we see the figure here or the clinker content, and even with what we can call an LC335, at 28 days, we can get the same strength as the reference Portland cement, which you can't do with this pozzolanic materials. So this is not just a nice idea in the lab, it's being produced full scale. In terms of calcination, we have to get the good temperature for calcination, around 700 to 850. Of course, this does demand some energy, but the CO2 emissions from calcining clay in a conventional manner are less than a quarter of what you have from producing clinker. And because of these lower temperatures, it is a technology that could be relatively easily electrified. So this is the first production we made in Cuba. We could take it to this block factory where they were producing blocks, and people could use it on a one-to-one replacement with no extra training, and the blocks had the same properties. We could produce nice flowable concrete, build this house where the render is also in LC3. Then we made a production in India, again, making blocks and pavers. And we built this house, which is all out of LC3. And with this one house, we could save 14 tons of CO2. We also did demonstrations in more demanding applications like precast hollow core slabs. We could meet the demand. Just to look briefly at some of the advantages and disadvantages, one thing people sort of throw their hands up in horror about is the color. People say people are not going to buy red cement. Well, you could say if it's lower CO2, that should be an advantage. But at any rate, if you don't want red cement, you don't have to have red cement, because this is the raw clay here. This is the normal calcination you would do like in your laboratory. You still end up with a red color. But if you do this in an industrial process, there are very simple technologies to control the color. And this gray color came out of an industrial production in the Ivory Coast. People are worried about the carbonation. Yes, like all blended cements, it will carbonate faster, but the data we've got so far show that you can still ensure the good service life according to all the kind of norms around. So it's good in the reasonable exposure conditions. Workability, here you can see very, very good workability. Normally you would have to maybe use slightly higher amount of superplasticizer, but the good news is that the admixture companies are now coming out with new superplasticizers, and these perform much better. And you get very, very good cohesion. So for example, if you have a self-placing formulation like here, your overall admixture demand may be lower. In terms of chloride ingress, we see here a series of mixes. This is the reference Portland cement. These are the mixes with slag. These are the blue are the mixes with fly ash, and purple are the mixes with calcined clay. And you can see how the chloride penetration is dramatically reduced in the case with calcined clay. So people say this is due to the pore refinement. This is actually not quite true. Then they say it's due to tortuosity. And you know what you have to remember here is tortuosity is defined as the ratio of the transfer in a pure solution to the transfer in the sample. So it's kind of a circular argument. And you should not think that tortuosity is to do with a tortuous pore network. So here's the simple idea of tortuosity, that the path an iron has to take in this pore is longer than going straight through. That's true, but that's a tortuosity of about 4. And to get tortuosities like you saw in this last graph, around a few hundred, you would have to have a pore that went kind of like this, but that's impossible because, you know, you'd have other pores like this, and in the end you could go straight through. So what is forming these very, very low chloride diffusion is actually much more subtle and much more interesting. You can't even really get a good idea from mercury intrusion curves, because this shows mercury intrusion curves, but then you have to think about how many of these pores are actually saturated. No concrete in real life is completely saturated. And even at relative humidities of like 90%, the large pores are empty, so that only the pores smaller than about 7 nanometers still contain solution. And now we have to think, we have these 7 nanometer channels between these complex surfaces of CSH. And what is really happening is that we have interaction of the chloride ions, which slow down their migration due to these surface effects we don't yet well understand. We can get these properties much better in the field because we have a much faster reaction. And here's the proof in our exposure site. No alkali silica reaction, certainly at the higher levels, because we produce small amounts of alumina in solution. And best of all, you can actually save money. And this is actually what's going to be the main driving factor in this technology, because despite the fact that the planet is facing this climate crisis, unfortunately, business is business and people have to make money. And what's really going to drive people to take it up, particularly in places like Africa, is the fact they can save a lot of money. And we published a report, it's available online, which show these calculations for an integrated plant, but also for a grinding plant. And that's particularly interesting in Africa because they don't have a lot of limestone deposits. They can't make a lot of clinker. Most of clinker is imported. And therefore, it becomes very expensive. I had the visit yesterday from somebody who runs grinding stations in Burkina Faso and Togo and Cote d'Ivoire, where they're paying 3 or 4 times for clinker what a cement manufacturer does by producing it himself. And therefore, if you can locally produce clay, you can save a lot of money, but you can also save a lot of this transport of materials and loss of foreign currency for these countries. So now we're engaged with companies in more than 40 countries, 50 countries worldwide. We have the first productions coming online in Colombia, Ivory Coast, but I think in the next few years, we're going to see an exponential takeoff. We know trials are taking place in France, in Germany, in UK, in Switzerland. Very soon, 2 to 3 years, this is going to be available everywhere. I know I'm running out of time, but I just want to finish by coming back to this slide and emphasizing this is not the end of the story, because we have to go further. We have to follow these steps through reducing cement in concrete. And this figure we had in our UN report shows the huge dispersion of the amount of cement used to produce exactly the same concrete. I'm going to skip over these slides here and come to my conclusions. So what I really hope you can take away from this presentation is that we can't run away from Portland cement clinker. We're going to be stuck with this, and we're going to have to do carbon and capture and storage to some extent. But we can achieve a lot in the meantime, and we can do it very fast and at very large scale by incorporating supplementary cementitious materials, and particularly calcined clay, because moving forward, this is the only realistic option to extend the use of SCMs. And we can get good, very similar properties to CEM1 with up to 50% replacement, even higher replacements if we want lower grade cements. And we have a very positive impact on chloride resistance in ASR. So I think this is something we've got to get serious about. We now see, after me peddling this message, pushing this message for many years, it's really starting to catch on, and lots happening. Everybody says to me, where can we get it? And I have to say, wait, but now I can confidently say that, in 1 or 2 years, you will be able to get this everywhere. So I'd like to thank you for your attention, and hopefully you have some questions.
Thank you very much, Karen, for a very insightful, very thought-provoking presentation, as usual, very interesting. So actually, yes, our attendees have been very active in the chat. So I will just read some of the questions. One of your slides showing the CO2 emissions allocated to different industries. We have a question about if these values are global or UK, but I think the represented were global.
Yeah, these are global values. And I'm not standing by the fact that they're hyper accurate. I just got them by Googling. But, the message is not whether it's 8 or 9%. The message is all of these sectors are important, and we have to work on all of those.
Yes, thank you. So you already answered other
stores,
questions. Yes. So another question is, are the alkali activated cements a good option to reduce CO2 emissions?
Well, no, they're not, because you actually don't do anything. If you look at the examples in the field, they all contain substantial amounts of slag or high calcium fly ash, because you can make geopolymers with low calcium materials, but then you have a lot more of these problems, particularly like shrinkage. And the problem is we don't have any slag. This is what we have to face the fact about, that slag today is 8%. It's all used. So by displacing it from one application to another, you achieve nothing. And you maybe globally achieve a negative impact because you've got to make all these activators, and these activators are not CO2 neutral. So you do not reduce, it is not a good option. Please believe me, it is not a good option for the simple reason of the resources available. And, so I'm not arguing whether they're good materials or not. I'm simply telling you they cannot make an serious impact on CO2 reduction because we don't have any of these materials unused.
Yes, I agree that the current approaches are not as promising as some people is trying to advertise them. So we perhaps need to rethink the approach to those technologies. So another question is, has kinetic heat transfer method of heating limestone been considered or investigated to replace kiln natural gas radiant flame burners in the production of foam cement?
Okay, there are a lot of people looking at different methods to make cement, particularly from a view to what extent you electrify them. So there are developments in that area. I'm not going to go into them in detail, but just because you use a flame in this rotary kiln doesn't mean that it's inefficient, because now rotary kilns can very efficiently recapture the heat and feed it back further up the process. What is interesting in terms of new technologies is that by separating the step of breakdown of limestone and the step of the clinkering, you have a very good possibility to produce almost pure CO2. And of course, in terms of carbon capture and storage, which will have to occur to some extent, this then makes it much more efficient than things like direct air capture, because you already have your CO2 captured. You still have to find a solution to store it or use it. And, let's not get into use, because the problems here are the amounts. The amount we can reuse is minuscule compared to the amount we produce. So we will have to store it. So that's the real issue. But, there are technologies coming out there.
Thank you. I think the following question is quite specific. Do you achieve compressive strength for LC350 with a standardized test or with superplasticizer? So it's not very clear. But
yeah, so we use a standardized test. We use the EN196 mortar bar test. Depending on the type of clay, we maybe use some superplasticizer. I think this is legitimate because in concretes today, you're using superplasticizer. So these are compared at the same water cement ratio, which I think is a fair basis of comparison.
Okay, we have time for maybe a couple of questions. So I will skip some, so apologies to our attendees. One question is, was early strength development of LC3 checked?
So yeah, of course, we look at early strength development. I mean, that's an area we're working on quite strongly. The problem of working in the laboratory is that you don't have a lot of options in a laboratory for optimizing your grinding and blending. Ideally, what you want to do is to have your clinker fine, because that's what gives you the early strength. And, calcine clay and limestone are also very soft materials, so you hardly even need to bother grinding those. But in an industrial scale, these can be very, very nicely optimized. And then we know that you can get matching strengths almost at one day, but that's more difficult to do on a laboratory scale.
Another question is, what emissions will remain from the LC3 process, and what percentage of these can realistically be captured by CCS?
Yeah, so I mean, it's the same story. You will have some emissions from the fuel, but what's more interesting is that, as I said, because you've got a lower calcination temperature, it's a process that's much more easy to electrify. So there are already people working on calciners, which use electrical energy. And then it's the same story as everywhere else. You have to decarbonate your electricity grid. But, we know that is a general thing for everything. So based on conventional fuels, your emissions per ton of calcined clay are around 200 kilograms per ton compared to 850 for clinker. So that's already a big reduction, but we think it can go to zero if you electrify the process.
Thank you. And I think our final question, which is a bit thought-provoking, it says some countries claim that on an average, they have a higher clinker content in cement because they use SEMs at the concrete level instead of cement production. But if they use the same ratio of cement in concrete as the rest of the world, then then is there even a net CO2 reduction from the use of SEM?
Okay, well, look, I mean, at the end of the day, it doesn't really make any difference when you put your blending things in the cement or in the concrete. It does from a practical point of view that, you know, usually with these materials, it's quite important to get the right dosage of sulfates, and that's more easy to do in a cement plant than in a concrete plant. But from a CO2 perspective, what we should really be thinking about is the amount of clinker or the amount of CO2 in the concrete. And that then brings together these two levers that we have. We have already these two levers of reducing clinker in cement and reducing cement in concrete. And we need to work on both these levels to go to lower CO2 emissions. And I mean, many people have demonstrated that you can easily make good concrete with clinker contents down to about 180, even 150 kilos, as opposed to the figures of 300 to 400 we're commonly using today. So you're talking about, you know, possibilities to reduce CO2 emissions by 50% there.
Okay, so we're running out of time now. So I know there are a few outstanding questions here, but well, thank you very much, Karen, once again for your time. It was a very enjoyable presentation and very, as always. And also thank you very much to all our attendees, very interactive, very good questions. So we hope to see you in the next webinars that will be organized by the Transformer Foundation Industries Network Plus. So that's all for today. So thank you very much, Karen, once again. I'll see you next time.
Thank you.